Great. So yeah, so today I'm going to talk about joint work with Russell and Pagliazzo, Rex Slay, and Tony on reproducibility in machine learning. So first, let's talk about what we mean just informally by reproducibility and why it's important. Hopefully you don't mind me sweeping a ton of interesting philosophy of science types of questions under the rug with the slide, but we're just going to imagine the scientific process sort of comprises the following sequence of steps. So we have a researcher here who has a hypothesis that they want to test. Let's say their hypothesis is that some drug A is an effective treatment for disease B. Okay. So how are they going to test this hypothesis? They're going to design and execute an experiment to make empirical observations of the effect of drug A on disease B. Then perform some sort of statistical inference from the resulting data to make conclusions about the original hypothesis. And finally, they're going to report these findings to the broader scientific community by way of publication. Now, ideally, published scientific findings actually capture some sort of enduring real-world phenomena, right? So in our example, if the scientist reports in the publication that drug A has a significant effect on disease B, it should be the case that drug A truly does have such an effect on disease B, right? That's what we want here from our scientific process. But what does it mean for a drug A to truly have such an effect? Okay, again, I'm going to sweep a lot of really interesting philosophy of science questions under the rug here and just claim that what we mean is the observed effect should be reproducible. Okay, so it should be the case that if another team of scientists comes along and follows the same experimental procedure that the original team followed, that they would obtain the same results, right? This is informally what we want from our scientific experiments. We want this notion of reproducibility. Okay, so our interest in formalizing and studying reproducibility is motivated by the replication crisis in the sciences. The term replication crisis was coined in the early 2010s, thereabouts, with a sort of growing awareness that there are issues with replication of published findings across all manner of disciplines. So a 2016 survey published in Nature, which got a lot of attention, maybe some of you have already seen it, helped to shine light on the magnitude of this issue in the sciences. They showed that most scientists from just like the disciplines that they surveyed, here you can see you have some chemistry, biology, physics, medicine, earth sciences, other, that the majority of scientists had tried and failed to reproduce published results. Right? And so that's sort of indicated by these deep red bars here. It's trying to replicate somebody else's experiments. But many of them had even failed to reproduce their own experimental results, indicated by the lighter pink bars here. And this is troubling, right? This is not what we want from science just as a practice.
They didn't study TCS, I see.
I'll say, yeah, they didn't. But we will get into this as well. I think that we've got off easy for too long. And it's time for a reckoning, I think, is maybe the takeaway from this talk. We thought we were safe because we were so close to math, but I'm going to argue that we're not. At least not in machine learning. So concerns regarding reproducibility do extend to the computational sciences as well, and particularly in machine learning, which can be fairly experimental as far as computational sciences go. So in recent years, some major machine learning conferences have begun holding workshops and competitions to promote reproducibility of submitted work. There's this 2020 article in MIT Tech Review that actually goes into some interesting detail on some of the issues with reproducibility and machine learning specifically. Looking at some issues that are maybe not completely unique to machine learning, but some which I think are arguably specific to machine learning. That this field poses like some unique challenges to reproducing findings. So what are some of these issues? What are some of the challenges that we face in machine learning? So a typical experimental paper in machine learning might propose a new technique for a given learning task and demonstrate improvements over prior art through some sort of like benchmarking of their algorithm. This may involve collecting data on which to run the machine learning algorithm, as well as like writing and running code to actually do the training and the testing of the model produced by the algorithm. So just as our scientists from the previous slide, when they're writing up their findings, will need to write up their experimental procedure in order for someone else to replicate their results, a machine learning researcher would ideally make their code and data sets publicly available for others to study, right? That's sort of our experimental procedure. But there are already obstacles to this. So for instance, there are some misaligned incentives for industry researchers in some cases for making their projects open source, right? So maybe this is intellectual property that they don't want to make public. And another obstacle is simply tracking and reporting all of the randomness and hyperparameters that are used during training of a machine learning model. If you can think, if we're training some sort of neural network, the initial weights of internal nodes of this network, for example, are chosen randomly and can affect the results of training, right? So if we want someone else to be able to reproduce our procedure, we're going to need to make all of these, initial values or the randomness that we're using public as well. So this can be difficult to actually report. So these first two issues seem like reasonably surmountable with the right incentive structure and sufficient care, but there are other serious obstacles as well, like computing power and just like cost of hardware. So a large industry research group, again, like DeepMind or say OpenAI, has access to hardware for training models that is prohibitively expensive for smaller academic research groups. It may simply be impossible for a smaller group to follow the experimental procedure that's detailed in a publication and therefore attempt to replicate results. Just for, to sort of give you a number here, DeepMind Chief Executive Demi Hassabis estimated that the cost of hardware used for AlphaGo, but this is back in 2017, was around $25 million US. So that's, that's going to be way out of budget for a lot of academic research groups, and it's going to make replication sort of unappealing for many people. And another issue is proprietary or closed off data sets. So again, a research group like maybe Facebook or Google, or even like a medical center, if they're training a model on customer or patient data, there are very legitimate privacy concerns that can prevent researchers from making their data sets public, right? So I can't give you the data to use to reproduce my results if that's going to seriously compromise the privacy of someone whose data is included in that data set. Great, so what do we do about this? Like, we know that failures of published findings to replicate, like we know this is a serious issue, and we need replication to ensure that our scientific conclusions are reliable, are capturing some sort of enduring phenomena out there in the real world. And we have some ideas about what may cause experimental results to fail to replicate, but we don't have good formal definitions of reproducibility.
So just about the, of all the items you have there, I'm not sure why the second is a problem. I mean, given the description of scientific experiments in other fields, it seems like the randomness, it's good that it's different in different experiments, right? I mean, if you want to capture whatever, a real, world phenomena as opposed to what your data is about, then it's good that different researchers will be able to reproduce your model even if they have different randomness.
So this is a great point, and I think that that's, ideally, I think that, this is actually, I think, an issue with some machine learning research, is that people might be concerned that, a particular algorithm seems to be performing particularly well, but maybe that's just because you got lucky with some randomness that you chose, right? And so you'd like an algorithm to be able to work well across a lot of different random strings. However, for the task of like actually replicating a result, it'd also be nice to have those values published, just so that you can actually check to see that you can run the whole procedure from start to finish and obtain the same results, right? So I think that being able to actually pin down these values and make them public allows people to perform replication independently, and then if that fails, to isolate where failure of replication is coming from. Is it coming from randomness? Is it coming from the fact that you redrew your sample? And this is something that we'll be talking a lot about for the rest of the talk.
That's
So yeah, so
I was going to say that it would be better if over most choices of randomness, it was reproducible. But maybe this is even more, more relaxed that, for one choice of randomness. But it could be worse. It could be not just you got lucky, but that it was, many choices were tried until they found just the right choice of hyperparameter. Which...
Yeah, I guess there's also that. Yeah. But this is a good observation. There are a lot of sort of contributing factors to consider here. And when we talk a little, I guess, like when we start talking about reproducibility formally and looking at like our proposed definition, we can maybe come back to this a bit and sort of see, at least for cases that we're interested in, we'll want a sort of relaxed definition where we can like vary randomness, I guess. But yeah, we'll get to that later. Okay. So we have this issue where we want reproducibility, but we haven't really defined reproducibility. So we can't really have a theory of reproducibility because we have no definitions to study. We just have these informal expectations, like, well, if I follow some sort of, if I follow the instructions in your report, I should get the same results. And yeah, we sort of would like to have something a little bit more formal. And so we can say things definitively about the algorithms that we're using to, make inferences. Great. Cool. So it brings us to our work. We introduce a new notion of reproducibility as a property of algorithms themselves. So this might be like an algorithm that's used to train a model or to do some sort of statistical, any sort of statistical inference. So our notion specifically captures reproducibility for randomized algorithms under resampling. So this is going to informally require that an algorithm is going to output exactly the same result with high probability if its randomness is held fixed and its input data set is resampled from the same underlying distribution. So I'll be using this notation here like throughout the rest of the talk. So just go through it bit by bit. So we're going to be interested. We're going to consider algorithms that are operating on samples from sort of data domain X. Again, they're going to be drawing samples from a distribution over that domain. And they're also going to take randomness, right? So they'll have the sort of auxiliary parameter R here. And sorry, I'm trying to figure out how to use my pointer. Here we go. Okay, so now if I, oh dear, it's not quite what I wanted. That's fine. Can you all see? Yes, you can see my little red dot now, right? Great.
I think we put it before too, if it's easy.
Okay. So we have these randomized algorithms that also take as input a random string. And
so is there a universal quantifier over D, or this is for a particular D?
Great question. Yeah, so there should be an applied universal quantifier over D. So we're not going to make any assumptions on the distribution. We're not going to require that they're, well behaved or smooth or want to be the case that will be reproducible for any distribution. We don't know anything to begin with. Right. So we'll say that our randomized algorithm A is row reproducible if with probability at least 1 minus rho over 2 samples drawn from the distribution and a single random string R, that A on input, the first sample and the random string gives you the same result as A run on the different sample with the same random string, right? So we've swapped out our sample for a new one from the same distribution, but we're holding the randomness fixed, and we want to guarantee that we get the same output with high probability.
So yeah, so just to be clear, it's a universal over the random string R and over the distribution D, and the algorithm doesn't know D. Right?
Can I ask one question?
Absolutely. Yeah, this is a great time to ask questions because this is the definition we're going to be looking at for the rest of the talk.
Thanks. I thought that you were modeling a situation in which the algorithm outputs a circuit or a hypothesis or like a description of a function or something like that. And I wanted to ask if the fact that you enforce the algorithm to output the precise same output is just for simplicity, or does it capture something inherent?
So yeah, it captures something that we do care about in the case of reproducibility, or I guess like in sort of the application that I've been painting here. One I guess like application that we might be interested in is the case of, let's say, like hypothesis testing, right? So, or we can think of our algorithm as outputting essentially a binary decision, either reject null or fail to reject the null hypothesis. And so in the case where our algorithm is outputting a single bit, it doesn't really make sense to relax the definition to something where you say, okay, well, as long as it outputs, like something that's not too, it's like concentrated, or, as long as it's outputting like models that are like close together in some notion of distance, like this sort of doesn't make sense in this setting. And this is sort of one of our target applications. There are other reasons, I think, as well to care about it outputting the exact same result. So one of them, which we won't really get into, but is for potentially auditing private algorithms. So maybe we care about differential privacy, but it's actually hard to test in practice whether a particular implementation of a reportedly differentially private algorithm is in fact private. But it could be easier to audit a reproducible algorithm because you sort of know what you're looking for. You don't have some sort of distribution over models output by the algorithm. You know that there's a high probability output that you're looking for during auditing. And generally, you should just expect it to be make it simpler to know that you've succeeded in replicating results if you have, again, a sort of like not quite canonical, but like quasi-canonical hypothesis for a given for a given random string.
Thanks very much. That's excellent.
Yeah. Any other questions?
Yeah, I have one question. So actually two questions. So first, the binary string you're taking to be like uniformly at random, the binary string?
Yeah.
And the other question is kind of like, should I think of this as if there should be like a true answer? Because I mean, the answer shouldn't depend on the sample from this definition as it seems. Like if there is like, if you're trying to use your algorithm to approximate, to try to figure out the true value of some function, then the function is not really expected to have different values on samples, right? Because otherwise you could do
a single.
Yeah, you could do some silly distribution, like it's 1/2 one of the samples that's an instance of no, and 1/2 one of the samples that is an instance of yes, and your algorithm kind of doesn't stand a chance of satisfying reproducibility then, right?
So maybe I don't sort of, I thought I understood where you're going, but I want to make sure I actually do understand the question.
So the question is, so imagine that you're trying to use this algorithm to figure out the true value of some function that depends on the samples, and it's a yes/no function, right? Mm-hmm. 1 or 0. If there is some S1 which is an instance of yes, and there's an S2 that's an instance of no, then if your algorithm is going to approximate this function very well, it seems like it's not going to be row reproducible for silly reasons, right? Because
great. Okay, so
well, I guess it's a consequence of the definition that this algorithm, any reproducible algorithm, will answer the same answer.
Yes.
Almost surely. Yeah.
That was my point.
In particular, with probability 1/all, give the same answer.
Yeah. That was my point. I mean, the problem you're trying to approximate is that you're assuming that the answer is either yes for almost every sample or no for almost every sample, and you're trying to say the algorithm is good if it sort of finds this, right?
Seems like I think Jess is going to get to this, but it could output a function.
Yes.
Yeah,
no,
so I guess I'll also observe that the randomness is also doing some work here, right? So it could be the case that I have some random strings that are going to map every sample to yeses or map everything to no. I don't know if you were already taking that into account in the question.
No, but I think that over the randomness you look at S1, S2, and R, you have this an algorithm is row reproducible. In particular, it should imply that if you just randomize over S and R, single sample and random string, you should almost always see the same output. If you
Not really. I mean, the R might mess around whether you always see the same output, but I'm thinking of like fixed R. I know that the definition does not
Okay. So
allow for this, but sort of let's fix R for a second, and imagine that I would have a place, an S1 that has a yes and an S2 that has a no. I could do a very silly distribution that puts 1/2 of the mass on each of them, and then sort of seems like the row reproducibility fails if row is sufficiently small, right? Now, of course, I am fixing R, so this is not really correct, but you see the point that I'm trying to make here?
I think as you're trying to say, so you had to like a very, very bimodal distribution. So I guess the question is like, how are you imagining, what objects are you imagining the samples to be? Since the samples will be sort of like a collection, like a multi-set of examples from the underlying distribution.
Right. So imagine that I would just give you like 2 particular multi-sets, and my distribution D is with 1/2 probability it's the first, and with 1/2 probability it's the second. Right. So a very silly distribution. But it's such that if I use the first set, the algorithm outputs yes, and if I use the second set, the algorithm outputs no. Right. So that seems like a very silly thing to do, but
so I guess we're drawing elements for these samples IID. So I'm not sure how you're proposing putting like 1/2 of the mass on.
Can I say something? I might help. Can you hear me?
Yeah.
Yeah.
Thanks, Tony.
Yeah, so I think that the whole point of the definition is to disallow what you're saying, because in the applications S1 and S2, like Jess said, is, so think of it as like, I think she's going to get to this, but it's labeled examples of some say function from some concept class in the PAC learning setting. And so what you don't want is the algorithm A to memorize in any way, shape, or form anything about the samples.
right.
So
Okay, so
if I understand correctly, you're basically saying that you want to learn something about the distribution, not about the function of whatever you do out of the distribution. But then I still don't understand, why do we use the same R? Why don't we have R1 and R2 for the 2 sets? And we are basically saying that if we learn something about the distribution itself, then nothing should be fixed.
So this is a sort of nice relaxation of that I think allows you to construct, or like allows you to do more than you can do if you need to have. So if you allow R to vary, right, then you do essentially have like and if you want rho to be small, then you essentially do have like a canonical hypothesis, and that just might be that just might rule out your ability to do some learning tasks reproducibly.
But isn't that the entire point of not being dependent on the sample? Isn't not being dependent on the sample meaning that you are basically saying that what you want to compare here is some property of the distribution? This is not a property of the set S that I draw out of the distribution. This is something real about the distribution that I want to make sure that I can reproduce. But if you fix R, then as you said, it could be that A is just computing a function of R that is completely unrelated to.
All right, so I guess we'll see. I have like an example in some number of slides, sort of like silly task where there could be many good answers. Like there could be like many good functions that satisfy our objective, but we still want to select one of them such that we know that, once we fix the other parameters of our algorithm, we'll be able, we should see that specific specific result. Does that answer your questions? Like if there is a single correct answer, then like ideally we want to converge to that, like independent of randomness, yes, but there might be many like cases where there could be a variety of answers that we'd accept, and we just want to make sure that we're seeing the same one so that we can reproduce prior results. Does that answer your question? Or?
Yeah,
I think we just stopped you too early for this question. Maybe in a few seconds.
Probably with an example.
Reproducible algorithms exist in abundance if they ignore the samples. Right? They can ignore the samples. So the question is why we need examples to see that they do things interesting in, let's say, in learning.
Yeah, I guess like we'll look at yeah, we'll get to a couple of things I think fairly shortly. So maybe we can come back to this in a few slides if people are still skeptical. Great. Okay. So first I want to talk briefly about some other related definitions and just like do justice to previous work. So our notion of reproducibility was inspired by work on pseudo-deterministic algorithms, notably recent work by Grossman and Liu and Goldrake. And then their definition is a little bit different in that they sort of swap what we're holding fixed and varying. But that's all we're really going to say about pseudo-deterministic algorithms in this talk, unfortunately. There's also independent contemporaneous work by a group of researchers at Google, namely Ghazi, Kumar, and Manarangsi, who studied a very similar definition, sort of motivated by questions related to differential privacy. And their definition was itself a relaxation of a stronger definition, sort of akin to one of the ones that we were just talking about. We're imagining there's no randomness in the algorithm. Yeah, so this was also introduced in a study of privacy by Van Livni and Moran. So for the rest of this talk, we're going to focus on applying this definition to a couple of tasks. We're going to look at how to reproducibly compute statistics of a distribution. Notably, we're going to look at approximate median and also reproducible learning in the probably approximately correct framework for learning introduced by Valiant. Great. So let's get into statistics. So there's this fundamental task of approximating the median of some sort of distribution. Again, we don't know anything about the distribution D to start with. Oh, I see that this is. Okay. So really quick, I'll just define what I mean by approximate median. So we have some sort of tolerance parameter tau, and then we'll say that X is a good approximate median for the distribution D if, like no less than a half minus tau of the probability mass of D is on elements less than X and no more than a half plus tau is on elements that are less than X. So why do we care about this problem? Aside from the fact that it's a sort of very fundamental statistical task, computing medians of things, it also can be used to generically convert a non-reproducible algorithm into a reproducible algorithm, so long as the sort of starting non-reproducible algorithm is outputting a real value, something where like our median is going to be well defined. So how does this conversion work? Well, we can run our non-reproducible algorithm A, right? So here A takes a sample, outputs some sort of real value. We're not really worried about what A does here, but it has some sort of objective, right? So maybe it's estimating something and it has to estimate it within like epsilon, but no care, it's some objective. We're going to run it a whole bunch of times on different samples, independent samples S1, S2, Sn, and this will give us a sample that is itself from the distribution over outputs of A. And we can then run our reproducible approximate median algorithm on this sample, right? So we're now giving our approximate median algorithm a sample from a distribution over outputs of A, which satisfy A's objective. But now we're sort of choosing one reproducibly by nature of the fact that our approximate median algorithm is reproducible, right? So we just run A a whole bunch of times and then post-process with a reproducible approximate median algorithm, and we've now have a reproducible version of A. Great. So time permitting, we will look actually at the algorithm and how it works. But first, I just want to give a flavor of like why this isn't super easy. It's not completely straightforward, and then give our theorem statement. And we're going to come back to it later if we have time, which we might not. So why is this problem hard? Median's a fairly simple task. We can imagine, okay, here that we have, this is our distribution D, and we want to approximate the median. What goes wrong if we try to do like some sort of empirical estimation, right? So imagine we have some sort of sample S here, and we're just going to return the value 1.5, and over here we have some S prime and we return negative 1.1, right? These are clearly not the same value, and any sort of attempt to just like use our sample straightforwardly to get an empirical estimate of the median is going to suffer from the fact that it's incredibly dependent on the sample. So it's not immediately obvious what we do to make this reproducible, right? Without being very sampled. Yeah, like how we actually come up with a good approximate median that isn't completely dependent on the specific sample we happen to draw. But this can be done, and we give an algorithm for a reproducible algorithm for tau approximate median with the following sample complexity, right? So again, here tau is our tolerance, our accuracy parameter. Rho is the reproducibility parameter. And so we have this interesting like exponential and log star of the size of the data domain dependence here. Right, so notably this means that in order to be able to do this, our domain does need to be finite. However, given that it's finite, this number is probably not greater than 5. So this is kind of like a polynomial. And yeah, so I just want to mention really quick for anyone in the audience who's interested in differential privacy or is kind of curious where this log star dependence is coming from. Our algorithm is inspired by work of Nissim, Stemmer, and Vadan, Kaplan, Legit, Mansour, now, and Stemmer on approximate median or differentially private approximate median algorithms. And these algorithms are recursive. When they recurse on the length of the bit representation of elements in the domain. So again, we might get into this later, but for now, that's where we're drawing our inspiration from and where this interesting log star dependence is coming from. But for now, I want to make sure that we talk a little bit about pack learning and reproducible pack learning. So let's get into that real quick. Great. So I'm going to talk about the probably approximately correct learning framework of Valiant. And the sort of setup here is we have a concept class.
So
which is going to be
a question about this result. Is it possibly tight, this dependence on, or is it clear that one needs a dependence on the size of X at all for a reproducible algorithm?
That's great. So we're kind of working on this. There are related essentially matching upper and lower bounds in the differentially private setting that has just like not an exponential in log star the data domain, but just like log star, like log squared maybe.
Doesn't matter, but there is a dependence on X, and you don't know that it's essential.
Yeah, so we think, we can prove it. We think that we have a proof idea sketch for lower bounds that would give the it might be like a square root log star of the data domain, but we think that the data domain dependence is going to be in there in some form.
There's another place where log star comes in, and I don't know this differentially private works, but another place where actually recursion on the logarithmic recursion on the bit length representation of elements in this distributed, for example, I don't know, distributed coloring of cycle or bounded degree graphs. So
interesting.
If you don't know, I'll tell you about it later separately.
Yeah, that sounds great.
There it's tight, so yeah, I'll tell you about it.
Okay. I'm very curious because I think that there's like an interesting coloring related. There are like several proofs of the differentially private lower bound, and I think one of them also goes through coloring, but I can't remember the details off my head, so I'm wondering if they're related. Anyway.
Oh, sorry.
Sorry, no, go ahead.
Just about the previous result, can I ask a question? So does the reproducible algorithm output the precise same tau approximate median, or just with probability 1 over rho, 1 minus rho, outputs medians that are, tau over 2 close to each other?
Outputs the exact same value.
Exact same.
Exact same value.
It has
to make sure.
Discretize somehow. It has to, yeah.
Good.
Yeah.
Good. Thank you.
Cool. Any other questions before we go into pack learning? We have a notation dense slide ahead. Just want to prepare everyone for that. So we have some sort of concept class. There's a set of functions that we want our algorithm to be able to learn. Here learning is going to be like approximating. There are going to be Boolean valid functions over domain X. We'll have some distribution over the data. We'll use F to denote a particular function our target function from the concept class C. And then we'll say D is going to be a distribution over labeled elements of our data domain. So we have the same marginal distribution dx, d sub x here, but then we're going to label each of these elements with the function f. There would be some parameters for our learning algorithms. There'll be a delta parameter, which is a failure probability, is the probability that a learning algorithm outputs something useless with like no useful guarantees on accuracy. And that's where the probably in so probably approximately correct comes from. And there's also going to be an accuracy parameter epsilon. And this is the target accuracy that, you know, if as long as we output something useful, useful is that we're like epsilon close to the target function. And this is where the approximately correct is coming from. So we'll let A denote an algorithm that takes in a sample, a variable length, and also a random string, and then outputs an element from our concept class C. That's, at least in our setup here, that's what we're going to care about. And we'll say that A is a pack learner for concept class C if for all F from C, for all epsilon delta greater than 0 less than 1, and all distributions D, there exists some sort of values for N and L, such that A can take a sample of size S from D and the random string of length L, and output a hypothesis that agrees with the target function F on all but like an epsilon fraction of the distribution that we're trying to learn over. So this is our standard pack setup. This is what we're going to care about achieving with reproducible learning. So any questions about the framework here? I guess I have a few more things to say about it. Anyway, crucially, this model is going to let us quantify the relationship between resources that we care about, things like runtime of a training algorithm or machine learning algorithm, and sample size, and parameters that we want, like target accuracy and failure probability, right? Where we can imagine, oh, if we want to be really, really accurate or fail with really low probability, maybe we'll need to take a larger and larger sample. So this pack framework is allowing us to quantify these relationships. And moreover, we'll sometimes care about efficiency, where we'll care that our sample size or like randomness and also the runtime for A will only have a polynomial dependence on our target parameters like accuracy and failure probability. And also sort of the size of the concept class or some other invariant quantity of the concept class that we're trying to learn.
Shouldn't that be log of the size?
Log, yeah, probably log.
Yeah.
I'm sorry?
I think
Log
that's
the size
log.
of C. Log the size of C or the
Oh, yeah. Thank you. Okay, so let's give an example. I guess that this is one of the examples we were talking about before, but why reproducibility might be a challenge or why we don't like get it for free or something out of just saying that we have a pack learner. So imagine the following classification task. So we have some sort of target function F defined here that is, I'm going to take in a sort of pixel representation of a handwritten digit, and it should output 1 if its input represents a number that is less than or equal to 5, and it should output -1 otherwise. So if we're allowed to err on some fraction of the input distribution, it could be the case that there are many very good hypotheses. Maybe we have like some sort of hypothesis here that's correct on every element from this, from our possible input data set over here, except for this 1 4, and it just misclassifies this 4. And similarly, like we have another hypothesis that just misclassifies 7, other hypothesis that misclassifies this one particular 8. Okay, and we can imagine distributions over the data domain for which all of these are equally good. And our algorithm might output any of them, but we want reproducible pack learning. And so we want to make sure that if we fix the randomness to our algorithm, that we're only going to see one of these with high probability. So that's like the problem that we're trying to solve here with reproducible pack learning. Great. So what sort of results can we get for reproducible pack learning? So first of all, we show that reproducible algorithms that fit their training data have good generalization properties. So if we go back quick to the definition of pack learning, we care about agreeing with the target function f on an underlying distribution, right? But we're getting our function h by running a on some sort of sample from that distribution, right? So we want to know that if we run an algorithm on our sample, that it's still going to, and if it's very accurate with respect to the sample, that it will also be accurate with respect to the underlying distribution. And we show that you get this immediately if your algorithm that you used for training is reproducible. We also give reproducible algorithms for pack learning of half spaces with a margin. So this is a pack learning problem where the concept class is parameterized or fixed by a vector w, and so our data is labeled according to the sign of the inner product of w with input x, right? So you can just imagine if we have some sort of nice hyperplane separating our data into positive and negative examples, then w is just fixing that hyperplane, and we want to learn a good approximation to that plane. And we also give a reproducible algorithm for answering statistical queries, and we're able to show nearly matching a sample complexity lower bounds for this task as well. And statistical queries are great because they capture like a whole range of algorithms for pack learning. There are some exceptions, of course, it doesn't capture everything, but they're actually very, very powerful, and we'll show that you can simulate statistical query algorithms reproducibly. So let's get into statistical queries. So statistical query.
Maybe I'm
yeah.
just pointing out that the approximate median is a simple example of one of these.
I'm sorry?
Might be good for people who haven't seen this before to think of the approximate median you started with as an example.
Oh, of a statistical query? Or?
Yeah.
Yeah. Great. Yeah, so a statistical query is, first of all, I'll say that this is a model introduced by Kearns in '93 to try and understand how to learn under different kinds of noise, like noise models in the data. And a statistical query takes a labeled example to, we'll say, a value in 0, 1. And then a statistical query oracle given as input a query and parameterized by an underlying distribution and an accuracy parameter tau should output a value that is close to the expectation of the query over the underlying distribution. And again, there'll be some probability of failure delta here, where I'll put something that doesn't satisfy this tolerance parameter. Okay, so I'll note here that we can simulate statistical queries. They are real objects or statistical query oracles. So if we get a sample from our underlying distribution D that's size of log 1 over delta over tau squared, then we can essentially use a turn-off bound type of argument to argue that the following simulation mechanism works. So we give our mechanism M our sample and the query that it's supposed to be answering with respect to the underlying distribution, and it just empirically estimates the expectation of the query over the distribution using its sample. So any sort of statistical query algorithm, right? A statistical query algorithm is an algorithm that is not given access directly to a sample. Right? It's instead allowed to make statistical queries of some sort of mechanism like M. And say a statistical query algorithm is able to still meaningfully learn its target function, given only the sort of oracle access to information about the underlying distribution. But again, because we can simulate these oracles using a sample, then if we're given a sample as we are in the standard CAC setup, then we can run the statistical query algorithm and we can still learn. Great, so we're going to show that if we assume that we have, because we know we can simulate it, we have a mechanism for answering statistical queries of a somewhat tighter accuracy parameter. So we have like a better statistical query oracle that's not reproducible. We can use this to give us a reproducible statistical query oracle. We're just going to lose a little bit in terms of accuracy. So we'll have a reproducible statistical query oracle that I'm denoting. M is parameterized by, again, tolerance tau, reproducibility parameter rho. And for uninteresting reasons that are really just type checking for the definition of reproducibility, I'm now parameterizing the M by the statistical query as well. It's not taking it as input. We're assuming that M takes, we want a reproducible algorithm to just take a sample, and so we're sort of pushing that input to a parameter. So how are we going to do this? Don't worry too much about the specific value of alpha here. Just want you to see that it's not complicated. It's not a scary value. So we're going to pick a offset value in the interval 0 and alpha uniformly at random. And then we're going to use alpha and this offset to chunk up the interval from 0 to 1. Right? So a statistical query oracle is going to output a value in the interval 0 to 1. And we're going to discretize this output space starting from this random offset, alpha off, and then taking subintervals from that point on of width alpha. Now we're going to use our statistical query oracle with tolerance tau prime to estimate the value of our statistical query on the underlying distribution. So this is our oracle is going to give us back some value. And this value, again, because it's in 0, 1, is going to fall within some subinterval, right? That from the partition of the 0, 1 interval. So we're going to look at the subinterval that this value lands in, and we're going to return the midpoint of that interval. That's all we're going to do, right? So if you think about what we're doing here with this partitioning of the 0, 1 interval, is we're picking canonical representatives for all of the possible answers in the 0, 1 interval. And given that we now have these canonical representatives, we're then going to ask our statistical query oracle, hey, like what is the value that you would have given us? And then we're just going to round that value to the closest canonical representative, right? So we'll go through why this is reproducible in a little bit of detail, but informally, what we want to see is that, okay, as long as the statistical query statistical query oracle that we're invoking is giving us well concentrated values, then probably we land in the same subinterval of 0, 1. And as long as we land in the same subinterval, then we return the same canonical representative, and therefore we are reproducible.
So even for anybody who didn't follow the definition of statistical query, this in particular, like Tony said, is an algorithm for the median, a reproducible algorithm for the median. Just assume that the statistical query is just giving you the median up to some tolerance tau prime, and this will give a reproducible algorithm for the median, right? The median is a special case.
Yeah. So you're saying, sorry, what you're.
What I'm saying is that you could have, run your mechanism on some non-reproducible median algorithm with some tolerance tau prime. So you just get the median. You get some approximation of the median, which is good. And using this discretization, you'll find a canonical thing that's still close to the median. A little far off, but it's very close.
Yeah, and we can choose. We're going to choose our the width of the subintervals and the size of our sample to make sure that all of these quantities balance out, and we get our target.
Yeah, and the offset is
reproducibility.
just to make sure that the algorithm didn't tailor it to land always on a between two.
Exactly. So this is
in
yeah
the
the,
boundary of two intervals.
yeah. So this is exactly. So let's think about what can go wrong here, right? So like why is this reproducible? So again, if we have these green dots are sort of representing the canonical representatives that are induced by our choice of the offset here. So imagine that the expectation, the value that we actually care about, the thing that we're trying to estimate, lands right on a boundary, as I was saying. This is really bad for reproducibility, because then once we try to actually empirically estimate this, maybe we underestimate, we land in this subinterval, and maybe we overestimate, we land in this subinterval, and we're not going to be reproducible, right? And we're going to have a high probability of not being reproducible. But we chose this offset randomly. As Avi observed, we want this to be a random choice so that we can sort of bound our probability of landing in a bad region, of the quantity we actually care about landing too close to a boundary. So you can sort of imagine, like, what if we chose a different offset here? We chose something a little bit smaller. Well, now we've shifted everything a little bit to the left. This is still no good, right? Because now both of these red dots are still in different subintervals. But there are plenty of good values that we could have chosen as well. If we move it a little bit to the left, then we see that, okay, yes, both of these red dots are now within the same subinterval, and we'll return the same value with high probability. So let's go through a theorem and a quick proof, since it's fairly quick to show that this is both accurate and reproducible. So we're going to actually need to fix the value for tau prime here, right? Tau prime is the sort of tighter accuracy parameter that we needed from our non-reproducible statistical query oracle. And we're going to take our sample size large enough that we can essentially invoke a turn-off bound. And right, so then we claim that our mechanism described in the slide is going to be reproducible with tolerance tau and failure rate delta. So let's look at accuracy. Again, our turn-off bound is telling us that the statistical query that we're answering using empirical estimation from our sample S is going to be within tau prime of the actual expectation that we care about, right? And we're trying to make sure that we land within tau. Tau is larger than tau prime. So far, so good. But we don't just return this value here, right? The empirical estimation, we're going to tweak it a little bit because we're going to return the midpoint of the subinterval that it lands within. So this can further offset the value that we're returning by at most alpha over 2, because the subintervals are of width alpha. And we chose alpha to make sure that this works out, right? To make sure that once we chose alpha, I guess I can, and tau prime, such that alpha over 2 plus tau prime is tau. So great, we're going to be tau accurate. So let's look at reproducibility. Again, we want to make sure that we land in this sort of a good case where, if we imagine now that these two red dots are representing like the expectation minus tau and expectation plus tau, we know that as long as we haven't hit our failure, that our statistical query oracle is going to return something in this interval. And we want to bound the probability that the endpoints of this interval lie on different sides of a boundary. Okay. So first of all, if our original statistical query oracle failed to meet its tolerance bound, we can't really say anything, right? Because then for all we know, we got a value from it that is like landed in this subinterval. We got another value that's over here. We can't say anything about reproducibility in this case. And an invocation of our statistical query oracle will fail probability delta. So over 2 runs on 2 different samples of the algorithm, that'll contribute a total failure probability of 2 delta. So there's also the failure of reproducibility that comes from bad choices of the initial starting value, the initial offset, right? There are alpha possible values we could have chosen, or I guess like there's like an interval width alpha that we're choosing from. And then there's a bad region, right, of width 2 tau prime that we're trying to avoid. And so the total probability that we fail due to both endpoints of our interval being of the estimation being on different sides of a boundary, that's just going to happen with probability 2 tau prime over alpha, right? So again, we've just chosen this parameter so that the algebra works out, and adding these two together gives us row reproducibility. Great. So any questions about the statistical query procedure here? I wanted to give the details because it's pretty quick to go through, and this is also sort of like the like flavor of the one weird trick that we're going to use for most of our other results, right? So you can sort of cast all of our other results as some kind of randomized rounding. So really the name of the game is to find a useful discretization of the output space of your algorithm. And this discretization will be randomized in some way using the input randomness. And then select the region that you're going to output a canonical representative from, using sort of non-reproducible-ish techniques, but then round to the canonical representative within that region and output that canonical representative. So any questions? Okay. I have a couple of other things that we could talk about, but because we're kind of out of time, I believe.
You can take 5 or 10 minutes if you want.
I
don't know. What do you think, Tony? Call for your help here.
Yeah, I think it would be good to talk about maybe a little bit, maybe the threshold result a little bit, or
the hyperplane.
The hyperplane. Yes, sorry.
Yeah. I was going to ask about that.
Oh, okay.
We only have a few minutes, but just to see why, with an output space, it's not in an interval. Yeah. And maybe even the lower bound. I'm not sure.
Oh yeah, the lower. Okay, so I unfortunately I did not have slides for either of those topics. I have slides for. We can maybe talk about them anyway. But I have slides for the heavy hitters result and the approximate median result.
Whatever Alvira, whatever everybody else wants.
Yeah, I guess like what
Well, you can go through the slides and we'll ask you in the questions about the
okay.
other things.
Okay, sounds great. Okay, so right, so I guess another there's to build up to the approximate median algorithm, I wanted to just describe another subroutine that we're going to use, a reproducible subroutine for the heavy hitters problem. So if we have a distribution over domain X, we'll say that some element X is a V heavy hitter of that distribution if the distribution assigns probability mass at least V to that element. Okay. So just by way of example, let's say our domain here comprises these 5 elements, and these bars here represent the probability mass assigned by D to the elements. Then if I care about 0.25 heavy hitters of a distribution, and I'll say, okay, element X4 and X5 here are heavy hitters. This problem comes up in questions like search engines, estimating entropy of a distribution, also recommender systems as well. If you want to know, like, oh, what music are people listening to? What are popular items? And we show that there's a row reproducible algorithm for heavy hitters with modest sample complexity, polynomial, and all of the target parameters that will return a complete list of V prime heavy hitters of a distribution. So not exactly V, but for some value V prime that's chosen sort of by the randomness of the algorithm that's in the interval V minus epsilon and V plus epsilon. Okay, so using this to sort of, again, I just wanted to say what this was so we can use it as a subroutine for the approximate median algorithm. I want to give like a flavor of how this approximate median algorithm is going to work, because I think it's kind of interesting. So I'll describe a simplified version, which won't actually give it'll give us like a log dependence on the size of the data domain instead of log star, but it's easier to explain. So the proof idea is that we're going to imagine a binary tree where the leaves are labeled by all of the elements of our data domain, and nodes are, like the internal nodes of the tree are labeled by prefixes. So they're going to be defined by the path from the root to the node. So for instance, vertex V here is going to be labeled just 1, or this vertex here would be labeled 1, 1. This vertex would be labeled 0, 1. And the weight of an internal node is going to be the probability from the distribution D that an element X sampled from D has a prefix that it agrees with the label of the internal node for that prefix length. So yes, the probability that the label of the vertex is a prefix of an element sampled from the distribution. So our goal now is to find an approximate median, is to find a sort of approximate median prefix first. We want to find a prefix that isn't common for all of the elements in the distribution, but is common amongst many of them. And then we'll use this prefix to sort of generate 2 candidates for an approximate median, and then we'll do some tricks to figure out which one of them is the best median. Okay, so we can search the levels of the tree using our heavy hitters algorithm, right? So again, our heavy hitters algorithm is going to give us all of the high probability elements from a distribution. And so we can look at the distribution induced by sampling from our distribution, and then just only looking at like the first, K bits of the elements to find a heavy hitting prefix, right? So we need to be a little bit more careful than just a heavy hitting prefix. If we just wanted a heavy hitting prefix, we could take, either 0 or 1 and we'd be good, because surely everything starts with a 0 or a 1. We want to find heavy hitters, but then find a node that is a 1/3 heavy hitter, but doesn't have probability more than 2/3. Again, we'll need this to get an approximate median from our prefix. So again, once we found the node, we know that its label gives a high probability prefix for elements of D. So we'll now consider 2 possible candidates for an approximate median. We will take the label from this vertex and then pad it out with all 0s, and we'll take the label and pad it out with all 1s. And I claim that one of these will be a good approximate median. Where here, again, for the sake of simplicity, I'm taking a good approximate median to be, I'm being very liberal with what I mean by good approximate median. I'm going to say, okay, it's like, at least 1/6 of the mass of the distribution is less than or greater than this value, then I'm saying it's a good median. Okay, so we can now use, because we know that this prefix has weight in between like 1/3 and 2/3, we know that at least a 1/6 of the mass of the distribution has to be either smaller, or it has to fall in elements that are smaller than S0 or greater than S1. And so we can use our reproducible statistical query oracle to check exactly this quantity. We can say, okay, how many elements are less than S0? And if there are at least 1/6 of the probability mass is less than, it falls in elements less than S0, then this is a good approximate median, and we're done. Otherwise, we return S1. And again, we know because of the constraints we placed on picking V that one of these must be good. So again, this is going to give just like log dependence on the domain size, and we want to do better than that. We want this log star dependence. So to improve this, we're going to recurse. Okay, so we can imagine, rather than searching our tree to find and running our heavy hitters algorithm repeatedly to find a heavy hitting prefix, that we can imagine we have not a heavy hitting prefix, but a approximate median of prefix lengths, right? So we know that there's some length where, maybe like roughly half of the elements agree on a prefix of this length, and about half the elements disagree on a prefix of this length. So we'll consider this distribution d sub L, which is induced by sampling 2 elements from the distribution of interest D and returning the length of the longest prefix on which they agree. So if we had an approximate median for this distribution, this would tell us which level of the tree we need to look at to find this common prefix L of V, to find the internal node that we're interested in. And we note that if D is a distribution over X, where the size of X is 2 to the D, then this new distribution D sub L is going to be over a domain of size D. So we can make log star many recursive calls before we hit a constant domain size, and we can just exhaustively search for a good median. And so this is where the exponential dependence on log star of the data domain, size of the data domain, comes from in our sample complexity. Cool. So I just want to end with a few open questions. So I talked a bit about the beginning about our interest in reproducible hypothesis testing, and that's something that I think we're still really interested in looking at. We're also interested in reproducible algorithms for learning parodies. So like I said before, this statistical query learning captures a lot of the stuff you care about with pack learning, but it notably doesn't capture learning parodies. And so we'd like to have reproducible algorithms for this problem as well. Then what Avi brought up earlier, we'd also like some lower bounds, right? We'd like to know that our algorithm's at least close to optimal. And there's reason to think that we can use techniques sort of similar to those used in the differential privacy literature to obtain similar lower bounds. And finally, I think it'd be really cool to try and get, I don't know how to really know how to start trying to solve this problem, but it'd be great to get a combinatorial characterization of reproducible learning, sort of analogous to things like VC dimension for pack learning and little stone dimension for differentially private learning, right? Is there some sort of way that we can characterize classes that are learnable reproducibly? So I guess also there's the question of like, what are other definitions, right? It's like, what other pieces of this like reproducibility puzzle can we sort of slice off, formalize, and study, and which things might be more or less useful for our objective of sort of like improving the overall program of reproducibility in science. And that's all I have. Thanks very much.
Okay, thank you. Hard to hear everybody claps. So questions to Jess?
Well, I'll ask the question while everybody else is thinking of their questions. So one thing puzzled me early on, you, I don't know, it was one of the first slides, you said the 3 main things. You mentioned that any statistical query algorithm could be made reproducible, but the first thing you had on the slide was that if the algorithm did, I think what it said was if the algorithm had low empirical error over the samples, if you have a learning algorithm of that type, then it could be made reproducible. That confused me a bit. I don't know if I misread that slide. Oh,
I think what I was saying is like if you have a reproducible algorithm that isn't already a guaranteed pack learner, right? Like you just know that it fits its training data well, then you get for free that it's a good pack learner.
I guess I'm confused because I thought that basically a pack learner always, has the property that on a typical sample, it's going to have low, it's going to approximate the function well.
All right, but as I'm saying, if you have something that's not, that you don't know that it is a pack learner, right? Like in the sense that you don't know that it, if you didn't already know that it generalizes, right? If you didn't have some other way of arguing that, but you could argue that it's reproducible and has low empirical error, then you get generalization.
Oh, sorry, I misunderstood. So the original thing is reproducible.
Yeah. So yeah, you assume
okay.
reproducibility and then
Okay.
the pack.
Okay.
Yeah.
Okay. I missed that.
Okay, more questions. But I would like to hear a word or two on the hyperplane, the reproducible hyperplane algorithm. What's the rounding procedure you use there?
Okay, so you so we have 2. One of them I think is kind of an interesting curiosity that goes through some work on foams, but it ends up not being very efficient. But we show instead that you can do a coordinate-wise randomized rounding procedure, and this works as well. So I guess I should say, like, this doesn't work for giving you a high accuracy learner. So we're going to run this through a boosting algorithm. So we're going to use coordinate-wise rounding so maybe I should give more details first, but we're going to take our input data, right? So we're going to have like vectors that are labeled with which side of the hyperplane they're on. And we're going to use them to take like a sort of center of mass vector, right? So we're going to take like a weighted sum where something's, if we have a negatively labeled vector, then we'll just negate its value to flip it to the other side of the hyperplane. So we'll take a like weighted sum of our input sample, and then this will be sort of like a candidate weak learner. This is analogous to like the Cervedio style half-space weak learner from his like smooth boosting work. And then we can do a coordinate-wise rounding procedure to round to a sort of canonical representative vector, which might make us slightly worse of a learner. But we're going to assume that our data has good margin, so that we'll be fine.
But the margin has to be really big then, right? I mean, because if you are not going to use forms, then the accuracy of coordinate rounding will depend on the dimension of the data. And probably you don't want that.
Yes, yeah. So we do end up with a dimension dependence in the sample complexity.
I see. But if you use forms, then it doesn't depend on the.
But we end up with an exponential runtime then.
I see. I don't know why, but I believe you.
Because isn't the rounding procedure not known to be efficient?
Yeah. So like coordinate-wise rounding is easy, but the foams I think is a more it's like more of a more geometrical, and so it's a little like more optimized, and so it's solving like a lattice-y type of problem.
No, I don't. Well, I think it's yeah, I think it's efficient, but anyway, we can look into this.
I mean, that would be great if we were wrong about that.
No, I think this probabilistic algorithm is just is very simple from our form paper, but yeah. Anyway, we can look into this. Okay, more questions. More questions. All right, let's thank Joss again.